Hi and Assalamualaikum. My name is Siti Nur binti Muhammad Zulkarnain and I will present my final year project. The title of this project is Design and Analysis of Bodywork for NF-MKII car. I will explain a little bit about this project. This project focuses on bodywork of NF-MKII car. The type of car is segment A car with two-seater. A good aerodynamic design can lead to a better car efficiency and lower fuel consumption. We can see that most of the passenger vehicles have drag coefficient of 0.25 to 0.3. In order to get drag coefficient less than 0.4, some parameters need to consider such as turbulent model, velocity inlet, and aerodynamic design. So the objective of this project is to design and analyze the shape of bodywork to improve its aerodynamic efficiency. There are several steps to conduct the CFD analysis of automotive. First, we need product design specification of the car. The dimension of the car is stated in the slide, which is length 2985, width 680, height 1500, wheelbase 2000 and the track width 1505. All the dimensions is in millimeters. The first picture shows the car package of NF-MKII car. We can see that the engine compartment at the front, the car boot space, the driver and the chassis. The second picture shows the 3D model that will import to the ANSYS Fluent. We use ANSYS Fluent to conduct the CFD analysis. The third picture shows the domain that contains the 3D model inside it. We can see the left side is the inlet wall, the right side is the outlet wall. The size of domain is stated in the slide, which is front 2.5L, behind 12L, top 1.5L, and the both sides is 1.8L. Next, I will explain the boundary condition of the simulation. The table shows the inlet boundary condition. We use 4 different velocity magnitude, which is 20 meter per second, 30 meter per second, 40 meter per second, and the last is 50 meter per second. And for the outlet boundary condition, the table shows the variables. We use 0 Pascal for the outlet pressure. It is due to the pressure difference so that the velocity will flow from inlet to the outlet. As stated before, there are 4 different inlet velocity, which are 20, 30, 40 and 50 meter per second. The highest speed is 50 meter per second, which is approximate to 180 km per hour. This is due to follow capacity from powertrain department. The turbulent model used for the analysis is K epsilon. It is usually useful for free shear layer flows with relatively small pressure gradients as well as in confined flows. It can also be stated as the simplest turbulent model for which only initial or boundary conditions need to be supplied. Next, I will show the video simulation of bodywork in ANSYS Fluent. The video shows the velocity vector of the car. The plane moves from left to right, where the velocity vector acts on the car. Next, I will show the streamline velocity acting on the car. We can see that the streamline flows from inlet to the outlet. Next, I will explain about the result get from the analysis. The first picture shows the pressure contour of the car. We can see that the maximum pressure acts at the front of the car. The red color represents the maximum pressure. This is due to the condition of 3D model. In this stage, we didn't consider other front-end components such as radiator. In actual condition, there are a lot of holes at front end of car, which is to be coolant of engine compartment. Besides, it also can reduce the pressure impact at the front. from 4 different velocities. The higher velocity, the higher pressure difference between the rear end and the front end. Next, the picture shows the velocity vector of the car. There is stagnant region at rear end of car. The turbulent flow didn't distribute uniformly and caused the stagnant region. Based on the past paper, one modification, which is 14-degree rear inclination flow, can improve the turbulent flow. The third picture shows the dimension of the rear spoiler inclination, which is 14 degree. After simulation, the results show the turbulence distribute uniformly at the rear end of car. It gives good result for the car design.
Hi, I will explain more about the velocity vector based on the previous slide. So, imagine there is two types of vehicle. So, the front and the one at the back. So, if the front one move at speed 100 km per hour, due to the stagnant region at the back of the car, the second car can move same speed as the first one. This is due to the stagnant region and there is no pressure act on the second car. So this give bad impact to the first car, as if the first car brake, emergency brake, so the one at the second car which follow the same speed as the first car can collide together with the front car. There are some modifications that can be made to improve the car efficiency. One of the modifications that I've made for this project is the rear end spoiler inclination to 14 degree. We can see that the turbulence flow distribute uniformly at the back of the car. Besides, we also can make the rear end of the car to be more inclined. It can improve the turbulence flow at the back of the car. Besides, it can also reduce the stagnant region at the back of the car. We can see that most of the compact type car rear end design have a straight design like this. So in this case, the type of car is segment A car and for 2-seater only. So there is no problem to make it more inclined, as the most of the compact type car is a 4-seater and there is car boot space at the back. So we can make it to be more inclined at the back to improve the turbulence flow and reduce the stagnant region.
After run the simulation, there are several parameters get from the result. The two tables show the result extract from the simulation. The first table shows the pressure difference between rear and front end of the car. We can see the value of pressure difference increase along with the velocity. As stated in the previous slide, the higher the velocity, the higher the pressure difference between rear and front end of car. The highest pressure difference is 1639 Pascal when the velocity is 50 meter per second. Next, the table shows the drag coefficient of each velocity. We can see that the drag coefficient decrease as velocity increase. This can be proved from drag coefficient formula, which is drag force divided by half rho times area times velocity squared. From the formula, we can see that the velocity and the drag coefficient is inversely proportional. So, the higher the velocity, the lower the value of drag coefficient. Okay, I will explain the two graphs shown in the slide. The first graph is the drag force versus velocity. We can see that the drag force increase along with the velocity increase. This is because drag force is the resistant force caused by the motion of body through a fluid such as water or air. The drag force also acting the same axis as the velocity flow axis. The next graph is pressure versus velocity. We can see that the maximum pressure also increase along with the velocity. As stated in previous slide, The higher the velocity, the higher the pressure difference acting on the car. So, from both graphs, the relationship between drag force versus velocity and the pressure versus velocity is directly proportional. Last but not least, the computational fluid dynamics analysis of automotive was run on the bodywork with 4 different velocities, which are 20, 30, 40 and 50 meter per second. The analysis was conducted successfully in ANSYS Fluent. Other than that, CATIA V5 was used to model the 3D model of car. There are few parameters that cannot run due to limitation of computing, such as meshing size and a number of iterations. This is due to the student version of software. Some recommendation can be applied to improve efficiency of the car. First, we can install the diffuser and the radiator. The purpose of these two body kit is to be coolant, and it also can reduce the pressure impact at the front end of the car. Next, focus on the rear end of car, we can improve the design to be more inclined. It also can reduce the stagnant region and improve the turbulent flow at the rear end. That's all for my final year project presentation. I want to say thank you to College of Engineering UiTM Shah Alam, my supervisor Encik Muhammad Hanif Ahmad, and my friends. If there is any question, I've stated my email address in the slide and you can ask me through the email. Thank you and have a nice day.